Hello. Hello. Hello everyone. Welcome to the seventh tutorial of the course Nuclear Astrophysics. So, today I will mainly focus on some extra problems which was not in your assignment, but as the exams are coming, so I think that to solve some extra problems will be beneficial to you. And also I have gone through the materials of the 7th week. It is mainly most of the materials are based on theory. I mean, how the accelerator works, how the backing materials prepared, and what are the criteria or characteristics of those backing materials, and all those stuffs which are actually uh, I can say is you can cover it by watching those videos only. There are not much problems based on those topics. Those are exactly just pure theory. So I thought I would do some problems today. Okay, so at first I will do some problems, then I will come to the assignment at the last for the 7th week. And also I will discuss two type of accelerator mainly, which are very important. That is the cyclotron and the linear accelerator. All the other accelerator you can see it in any of the textbooks, but the most two important accelerator are these two, that cyclotron and LINAC, or the linear accelerator. And we will do some mathematical problems based on this two accelerators. So this is the thing which I want to cover today. Okay, so let us go to the problem directly. Now, till this 6th week you have gained much knowledge about everything. I mean, most of the materials has already covered. So you know everything, like the different type of nucleus model, the cell model, the semi empirical mass formula, ACMF, which are the basic model of nucleus. Also you have gone through different reaction, I mean resonant reaction, non resonant reaction, the cross section of those reactions. You have also done the nuclear burning stages of a star. I mean the different types of nuclear burning from hydrogen to silicon. Also the neutron induced reaction, the S process, R process, which are mainly dominating above the iron peak, that is with for those elements which has mass number of 56 and above. So all those you have done. And also you have calculated the the temperature required to happen the reaction, that means the proton proton reaction or helium helium reaction. You have done all those things, and I will do some problems based on the materials which has already covered in your previous weeks classes. Okay, so the first problem is that I will tell you a good book from which I have taken all these problems. Before the exam you can also go through that book, that is mainly based on the problems and solution. That book is mainly problems and solution based on the nuclear physics. So if you want to, I mean, do those problems, you can do it, I mean, before exams. Okay, so let us start with the problems. That the first problem today I have taken, that using only classical electromagnetism, give an estimate of the Coulomb term in the semi-empirical mass formula. So you know that semi-empirical mass formula which I have written in the last class. So there are several terms are there, and if we write the Coulomb term only, that Coulomb term will look like, let me use this blue. Yeah. So Coulomb term, that looks like AC Z into Z minus 1 divided by A to the power 1/3, where Z is the proton number and A is the mass number and AC is the constant. So actually we want to find that constant AC by some approximate idea of the classical electromagnetism. Okay, so this formula I can write it as AC Z square divided by A to the power 1/3. Here the assumption is that Z minus 1 is equivalent to Z. This is just an assumption. So suppose if you have higher number of Z, that is 50 and above, then your 50 and 49, you can approximate that 49 as 50 also. So this is just an approximation. You can use z into z minus 1 in this problem also. The result will not differ by a very large amount, but you can do it. For simplicity, I assume that z minus 1 is equivalent to z. Okay, and this, and suppose this is my nucleus, and the charge of the nucleus is q. That means the total charge of the nucleus, which is coming from a cumulative effect of different nucleons. Okay. So that is q, which is the total charge of the nucleus. Now from electromagnetism says that electrostatic energy for a sphere with a total charge of q, we are considering the nucleus as a sphere. So we can write the electrostatic energy as 1 by 4 pi epsilon 0, and 3q square by 5a, where a is the radius of that particular thing. I mean, this is the a. If it is center, suppose it is center, so this is a. So this can be written, you can, I mean, if you have done your electromagnetism course in first year of your graduation or second year, you know how to, this exact form of the expression, which can be written for the electrostatic energy of a sphere which has a total amount of charge capital Q with a radius a. That can be written. Very briefly, I will tell you from where that come at the end of this problem. So what we actually do is that this electrostatic energy, we will equate this with the Coulomb term, because that Coulomb term is also a correction of the energy. That means the unit of the Coulomb term is also energy. So we will compare these two terms. This 3q square by 4 pi epsilon 0 1 by 5a is actually ac j square a to the power 1/3. This is the comparison. Okay, and also you know that q, which I have written here, the total charge of the nuclei, that can be written as z times e if your proton number is z, because all the charge of the nuclei is due to the proton. Neutron is the uncharged particle or the neutral particle. So q can be written as ze if we put that q is equals to ze, that is z square divided by 4 pi epsilon 0 5a is ac j square a to the power 1/3. So now you can see why we have taken that approximation z into z minus 1 is equals to z square, because of this thing that we can cancel over the z from both sides. Okay, so this will give that your AC is actually I have written 3 by 5 e square by 4 pi epsilon 0, and okay, and there will be 1 a to the power 1 by 3rd term here and a term here, right? 3 by 5 and 4 pi epsilon 0 e square, a is there, and a to the power 1 by 3rd is there. Okay, and another thing, that the radius of a nuclei can be written as r0 a to the power 1 by 3rd, right? This has been done in the very first or second class, that the radius of a nuclei can be written as the power law, which that as a function of a, that is the mass number, which goes as a to the power 1 by 3rd with some constant r0, and the constant value was 1.3 femtometer approximately, right? So that's why we can write this a as r0 a to the power 1 by 3rd. So a to the power 1 by 3rd, a to the power 1 by 3rd also cancel out. So you can see that the z dependency and the a dependency is cancelled out from this equation, and it will be just 3 by 5 square by 4 pi epsilon 0 into 1 by r0. Okay, for r0 we will use that 1.3 femtometer unit. Now one important expression while doing many calculations of nuclear physics is very important. That's why I will ask you to remember whenever doing some calculation, some mathematical calculation, and you are getting this expression in your calculation, E square by 4 pi epsilon 0, where E is the electric charge of the charge of an electron, and other parameters, okay, the constants pi and epsilon 0. So whenever you come across this type of expression, a good thing to remember is actually it can be written as alpha h cut c, okay, where h cut c, alpha, or everything are constant. If you can remember this particular expression, that is fine, that is very good. Otherwise you can just put your value of E square, the value of epsilon 0 in the same unit. If you are using SI, then put everything in SI, or if you are using CGS, put everything in CGS. So it can be written as 1 by alpha alpha HC, where alpha is the constant, which is 1 by 137, okay, which is a very famous constant of nuclear physics, and this can be written as 197 by 137 MeV femtometer. If you can remember this particular expression, it will be very fruitful, very useful for your calculation. I am again saying, if you can't remember, no problem, just put your value of E and pi and epsilon, you will reach the same value. But in MeV femtometer unit, it can be expressed like this, that I will put in this expression. It is for simplicity, okay. 3 by 5th into 197 by 137, it was in MeV femtometer, and R0 you know 1.3 femtometer. So femtometer cancels out, and the result will come into MeV. The main purpose of doing this thing, expressing the square by 4 pi epsilon 0 in MeV femtometer, is actually when you calculate the AC or other constant, AV, AS, which was the constant of volume term, surface and surface term respectively, those constants are mainly given in MeV unit. So that is the main reason that we are converting that we are going in a unit system which gives me the value of square by 4 pi 0 as in MeV, okay. So if you do it, you will get 0.7 MeV, which if you see it in the any book, that it is close to this value, that AC, some approximation we have calculated it as 0.7 MeV, okay. So this is the result. Now if you ask how I have written that electrostatic energy, so this is the result of this particular problem. But now I am saying that how I am writing that electrostatic energy is 1 by 4 pi epsilon 0 3 q square by 5a. So that can be understandable like this. So it is a very basic course of first year or second year graduation, I am again saying. So suppose let the radius of consider that we are making the nuclei by collecting charge from infinity. That means we are gathering charge which are distributed at a very large distance at infinity, and we are taking that charge from infinity to a particular point, and we are creating the nucleus. This is the understanding. And let the radius at any stage of this whole process, that taking that charge from infinity to that particular point. So let the radius at any stage of this particular process is r, okay. And to increase, very quickly I will write it, to increase the radius of the nuclei, radius from r to r plus dr. That means at first it was like this, I am collecting charge from very large distance, suppose. So this will increase because I am collecting the charges from a very large distance. So the radius will increase, and to increase the radius from r to r plus dr, we require to bring an amount. This you can find in any book, any electrostatic book, of charge dq, that is rho 4 pi r square dr. So here rho is not the matter density, it is actually the charge density. So if your sphere have a total charge of q and volume v, that means q by v is the rho, that is the charge density, not the mass density. So don't confuse it with the mass density. Okay, it is I am saying for a constant charge of capital Q. Now so the amount of charge, so the work to do this whole process, the work is required, that can be written as q by 4 pi 0 into dq. Okay, and if you put your dq here, so if you don't, I think you can go through any book and you can understand it. So it will be 4 pi rho square 3 epsilon 0 r to the power 4 d4. Okay, yeah, 4 pi r square. Yes, that means we have written everything in rho. So this q we have also expressed as 4/3 pi r cube into rho. Okay, so this q has been written as 4/3 pi r cube into rho, as rho was my charge density. That's why you can see this expression is solely dependent on rho and the q is not there. So the total work, that means to make the nucleus from a point to a radius of capital A, small a, that is, it will be just the integration over this. Okay, and if you do this integration, I will not do it, the result will be 4 pi rho square 3 epsilon 0 a to the power 5 by 5. And if the nucleus now has, we have constructed the nucleus with radius a, so at the end of the construction of the nucleus, the volume will be 4/3 pi a cube, the charge density is rho, that will give you the total charge at the nucleus, that is capital Q for our problem. So if you just replace this rho here in terms of capital Q, then you will get the result 1 by 4 pi epsilon 0 3 q square by 5. So that is how we got the electrostatic energy of a nucleus is actually 1 by 4 pi epsilon 0 3 q square by 5. If you can remember it, it is very useful for your different type of calculation. Okay, so what we have done, that suppose we had a point here and charges are distributed here. Suppose charges are distributed here. I mean, this is infinity literally, because okay, and we are bringing one charge, it will gain some radius. We will bring another charge, it will gain some I mean, it will increase, the radius will be increased, then another charge. That's how the radius is increasing, and finally we are getting from we have started from a point and we are getting a nucleus with some radius a. So that is the understanding of this particular formation. Okay, and from that you can calculate that 4 pi say 3 q square by 5. This is the thing what I have used here, and we have calculated I mean, we have compared or equated this electrostatic energy with the Coulomb term, which is coming from the semi-empirical mass formula, and by comparing these two terms, we have calculated the AC, which is the constant term of the Coulomb. Okay. So this is a very simple problem, and this type of problem can appear in your exams also. Okay, so this now I will show you the book from which I have taken this problem. So this is the book. This is a very good book for problems and solution in nuclear and particle physics. If you want, you can go through that book, and it is the Google Drive link. So this in this link you can find the book. This is my link, actually my Google Drive link, and if you want to download the book, you can do it from this Google Drive. So I will ask you to go through the book if you get some time, or if you want to increase your knowledge. Okay, so this is the Google Drive. I think the NPTEL committee will also share you the Google Drive link, and you can find it there. Otherwise, just mail me if you want to. If you don't have access, I will forward the link to you in email address. Okay, so just mail me if you want, any of you. But this book is a very good book. It is iisc.ac.in. Saurabh Bhadra @iisc.ac.in. I will give you the access of this book. Okay. Now coming to the second problem is in more in the scenario of an astrophysics. You can say that we just a second. Yeah. So what a neutron star is an astrophysical object with a density similar to that one of a nucleus. So you can see it is a comparison between the neutron star and the nucleus. Knowing that its typical mass is of the order of solar mass. So a neutron star have given which has a density rho similar to nuclear density and mass is given as 2 in 1 solar mass. Okay. This is the information given in the question and we have to calculate the radius. So this is a very simple problem, but to brush up your previous knowledge I just take a few problems, and many good problems are also in that book that you can find. Okay, so actually the nuclear density if you calculate for a typical nuclei, that will be of the order of 10 to the power 14 gram per cc centimeter cube. Okay, and if you it is of the order, that's why I am putting that similar sign. And if you want to use a more realistic, more appropriate value, so it will be roughly 2.3 times 10 to the power 14 gram per cc. Okay, this is a typical nuclear density. Sometimes you may ask to calculate the nuclear density itself from the mass and the volume of the nuclei. So that's why I will just briefly show you that rho is m by v. This is the matter density. Don't confuse this rho with the rho of the previous problem, because in that case the rho was the charge density, but here it is the matter density, the general matter density. So m equals to rho by v, rho equals to m by v, and you can write that m, which is the mass of the nuclei, as a times mp. Okay, because your nucleus is made of proton and neutron, and the total number of proton and neutron is a. And here one assumption we have taken, that neutron and proton has almost similar type of mass. That assumption is there, that mass of neutron is similar to mass of protons, that we have taken. Okay, so AMP, and that volume will be 4/3 pi r cube. R cube, you again know that r is r0, a to the power 1/3. We will use that r0 cube a. So a will be cancelled out. That's why you can see that the a are getting cancelled out, and now everything which is in the expression, that is mp, capital R0, all these are constant. That's why the nuclear density for any element is generally a constant value. Typically it is a constant value, and like this. So if you put that just a second, yes, so that will be 3 mp by 4 pi r0 cube, and mp is actually mass of proton, 1.67 10 to the power minus 14 gram. 4 pi r0 is 1.3 or 1.2 femtometer, whatever. This is in the range. So if the question is there, the value of r0 will be given, so put that value. Here I have put that 1.2. Okay, so this will give you 2.3 into 10 to the power 14 gram per centimeter cube. This is a typical density, and the most important thing is it don't depend on a or z or anything. It is an independent quantity, because you can see that a from the denominator and the numerator cancels out. So this is the typical density of a nucleus, and we have to calculate the neutron star radius. Okay, so the neutron star radius, let's say r. So 4/3 pi r cube rho is actually equals to mass of the neutron star, and in our question it is given 1 solar mass. 1 solar mass means 2 into 10 to the power 30 kg. That's why from here you can calculate the R, which will be 3 into 2 into 10 to the power 30 kg divided by 4 pi and the rho 2 point. So here it is in kg and the rho I have calculated in gram, so you have to convert the kg into gram. So if you multiply with another 10 cube, that will convert the kg to gram. Okay, gram, and cc is there, and there will be 1 by 3. Okay, so if you calculate this particular thing, you will get it as 12.8 times 10 to the power 5 centimeter, okay, which is typically 12.8 kilometer. So you can see from a very simple assumption that the mass density of a neutron star is in the range of the the density of the neutron star is in the range of the nuclear density, and by assuming a typical mass of a neutron star, that is 1 solar mass, because you know that neutron star is the remnant of a star which has been gone through the explosion. So the core is only in that so the core of the sun has converted into neutron star. That's why it has a very less mass. All the most of the mass has been blown away by the supernova. That's why the typical value of 1 solar mass, using that and the nuclear density, we have calculated the radius, which is of the order of 12.8 kilometer. And if you go through the HR diagram, I will ask you to go through the HR diagram. You can see the position of white dwarfs are in the lower part of the main sequence, and from that you can also calculate the radius of a white dwarf. And white dwarf and neutron star are almost similar type of object, not same objects. I mean, in terms of mass and radius, they are similar type of, and from there you can also calculate, and you will find that a typical radius of a white dwarf is also 10 to 20 kilometers. So these two are consistent. Okay, so this is a very simple problem. Just you have to calculate the R from this particular equation. For third pi r cube rho equals to mass. Okay, so this is done. So first two problems we have already covered, that the Coulombic term problem and this neutron star radius. Okay, now we will go to a third problem. All these problems are from that book. Okay, so a deuteron gas, that means deuteron nucleus mainly 1H2 is heated at temperature T, and you have to calculate for which temperature nuclear process occurs. You have done this type of problems, many problems in your assignment also, just to brush up. As I have said, it is a class just to brush up your previous understandings. So that's why I am doing this, to give you, so that you can remember, yes, we have done this, and this is, I can do it in the exams also, so to brush up your memories. Okay, so what is the problem? That a deuterium gas is there, and we need to calculate the temperature for which the nuclear process occurs. That means two deuterium will interact and they will make some products. So which product, that is another case, but we have to calculate the temperature at which temperature this reaction occurs. Okay, so as deuterium gas is there, that means deuteriums have some kinetic energy and they are having some velocity also. Okay, so the kinetic energy Ke, so I am writing Ke for kinetic energy of each deuteron is half mv square, where m is the mass of the deuteron, v is the velocity of the deuteron. Okay, and this is the energy, and the reason of this energy is actually the temperature of the gas. The thermal energy which is giving its velocity, which is the reason of the velocity, because thermal particle has some velocity, so it will be of the order of kT. Okay, where T is the temperature of the gas and K is the Boltzmann constant. Now in lab frame, suppose you are in lab frame, two deuteron is coming from different I mean from opposite direction, and they are going to do some reaction. Now if you are sitting on a deuteron itself, on a one deuteron suppose, then that deuteron will look that another deuteron which was here, it will come with the velocity which is different from the lab velocity. First of all, I will say which is different. So if you are in lab, the velocity is v, then two deuteron with velocity v is coming together, I mean coming towards each other. But if you are sitting in at this deuteron, you will see that this one is coming towards you with the velocity of 2v. Okay, so actually from the lab frame we are transforming our frame to the frame of the deuteron itself, any of the deuteron, and it will see the other deuterons is coming with the velocity of 2v. That is the understanding. Now if that happens, then the total energy which is associated with that particular reaction will be half m 2v square, right? That is 1 by 2 half mv square is as there, and a 4, so it will be 4 times e, where e was a energy of a particular one deuteron in the lab frame. Okay, so 4e, it is I mean a more I will say appropriate calculation if you go to the deuteron frame. Okay, so this was the thing, and as you know that my kinetic energy will be such a way that it can overcome the Coulomb potential between the two deuteron, then the reaction will only occur. So this 4e, which is the energy associated with the reaction, which can be written as 4 kBT also, that is actually the square by r minimum, where the r minimum denotes, if r minimum is 0 ideally, that means the reaction is happening. Okay, and this is the closest approach. That's why it is called the Coulomb barrier of the particles. You have done it many times in the previous week's class also. So from here we can calculate that T is 1 by 4 pi epsilon 0. That means, I mean, this is actually this deuteron, if they have a distance r, then the potential will be square by 4 pi epsilon 0 r. So from there it is coming actually, which is the Coulomb barrier we say. So that is square by 4 kb. So here you can write kb and r minimum. Okay, so just a second. Yes. So r minimum we typically assume it. I mean it is not kb is given. So yeah, that was that's why I was looking for. So here hint. So see the hint that nuclear interaction is possible if the distance between deuterons of the order of 1 femtometer. So it has been given what will be the value of r minimum. Some value should be given, otherwise you cannot calculate. Okay, typically you can take it as 1 femtometer if nothing is given in the question, but here it is already given. So our r min is 1 femtometer. That means 10 to the power minus 13 centimeter. It is already given. We will use that, and you can see again we are getting that particular term. So this term is very important. This is square by 4 pi epsilon 0. I have told you in the first problem itself that this is square by 4 pi epsilon 0. Yes, anyone have Shami, do you have any question? Okay, so by mistake I think the raise hand option was clicked. Okay, so as I was telling that square by 4 pi epsilon 0, which is alpha h cut c, it is a very important expression of nuclear physics mathematical problem. So here also we will write that value which I have mentioned. This is for, I mean, for simplicity, and for you can solve the problem in a much quicker way than the if you go to put square epsilon 0 everything. That's why I am telling that value. And kb is given 8.6 10 to the power minus 5 in ev. So it is in EV and here it is in MEV. If I want to calculate, cancel out, then I can convert that EV to MEV, just multiply with the 10 to the power minus 6, so it will come in MEV by K, and again the R minimum is given as 1 femtometer. You don't have to go to the 10 to the power minus 3 value, because femtometer and femtometer will be cancelled out from the denominator and the numerator itself. Okay, and if you do this calculation, MEV will also be cancelled out, the Kelvin unit will be there, and it is 4 into 10 to the power 9 Kelvin if you calculate roughly. That might be 4 point something, in integer I am writing it as 4 into 10 to the power 9 Kelvin. So this is the temperature required to occur the reaction, that means two deuterium will come and make a helium. Mainly it will, I think, make one helium atom. So whatever that the product is, the main theoretical understanding is that this is how we can calculate the temperature for a reaction to happen, for any reaction. For a generalized scenario, you can calculate it for any reaction. Okay, just the change will be in the you can see in the R minimum, it will be given in your equation, and if there is a particle which has more than one proton, here actually the deuterium has only one proton, that's why we have written it as E square, but if it has more than one proton, then E square will be substituted by Z square. So the Z value, which is the proton number of different nuclei, will come into the picture for different type of calculation. If it is oxygen, then the Z will be 8. So in place of E square, it will be Z square actually. Okay. If it is oxygen, as I was telling, it will be 8. If it is carbon, it will be 6. That's how the calculation will change. Otherwise, everything is same. Okay. So this is, you can take this example as a generalized scenario for any of the reaction, and for the calculation of this type of question, what is the temperature to occur a reaction. Okay. So the change will be just this Z. Okay, so this we have done, that 4 into 10 to the power 9 K temperature is required for the deuterium gas. Now we will go to another problem. So 3 problems I have already done from that book, which may help you in your exams also. Okay, so this is a question of neutron rate. Okay, I will come to this problem a little bit later. Okay, not right now. Now let us go to another problem, that is the threshold energy problem. I have written it like this, so there is nothing called threshold energy problem. So what we will do, that we have calculated the Q value of a reaction. Okay, we can calculate the Q value of a reaction. Now that we have done, what new we will do this in this problem is we will find out what should be the minimum kinetic energy of the target particle, so that the reaction happens. It is not true that with any type of energy of the target projectile, if it is not the target, it is the projectile, which particle goes towards the target. So what will be the minimum kinetic energy of the projectile particle, so that the reaction occurs. The reaction will not occur for any value of the projectile energy. It has some threshold value. If the kinetic energy is greater than the threshold value, only then the reaction will occur. That we will do. Okay, so for an example, similarly, it is also one type of you can think it as a general type of problem, and you can do the same procedure for any of the reactions. We will take one particular reaction. So use blue. 19 fluorine reacting with neutron, giving 19 oxygen. This reaction, and that means if we can write it in this way, 0N1, okay, 0N1 plus 19F that is giving, I am not balancing both sides with proper way, so this is the main reaction. Okay, so so in our case this is the target and it is the projectile, and this is the daughter, or you can say product. So we want to now calculate what should be the minimum energy of this projectile so that the reaction occurs. That means the minimum kinetic energy. That means the K minimum of the projectile we want to calculate. How we will do that? Okay, so let us, for simplicity, I am writing this as x plus x as y plus y. That means small x is neutron, capital X is fluorine, capital Y is oxygen, and small y proton. For simplicity, otherwise I have to write every time 19F, 19O, 1N. That's why I am writing it like this way. And if this type of equation you come across of this type of equation, the Q value is generally calculated by this. You know that mass of the reactant minus mass of the product. If it is in AMU, if the mass is in AMU unit, then we have to calculate with a 931.5 MeV to get the final result. It is in AMU unit. Okay, and suppose the values are given. Okay, so suppose your value of X, that is mass of 19 fluorine, is 18. I mean these values will be given. 404 U is the AMU unit, or you can write AMU. So it is in U unit. M small x, that is mass of 0 and 1. It is 1.008665 U. M of capital Y, is mass of 19 oxygen, that is 19.003577 U, and mass of small y is mass of proton 1 P1 you can write. So that is 1.007825. So these values are given. Just put it here. I will not do. Just put and do the subtraction and addition. You will get the value as minus 4.0362 mm. So here the Q value is negative. You have seen that Q value may be positive, may be negative. So that depends on the endoergic or exoergic reaction. So that means whether we have to supply energy or we will get energy from the equation. That is the separate thing. I will not go into that. Now we have calculated the Q value, but our focus is, or our target is, to calculate the minimum kinetic energy of the projectile, which is called the threshold energy. So how we calculate the threshold energy, I will not go into the details of the theoretical understanding, because this type of problem you may face in the exam. Here where the theoretical understanding, you can go through any of the nuclear physics book. Okay, but I just want to do a example, I mean problem. So the kinetic energy minimum can be calculated, the mod value of Q. That means if it is negative, we will just take the value, and if it is positive, then the value is itself positive, and that is 1 plus mass of x by, I mean mass of small x by mass of capital X. That means this you have to remember. This you can find in any of the book, that the minimum kinetic energy of the projectile can be calculated by multiplying the Q value with the with another, I mean term, that is 1 plus mass of the target, mass of the projectile divided by mass of the target. Okay, so remember this in this way: 1 plus mass of projectile by mass of target, and this must be multiplied with the mod Q, which was the Q value of that equation. If you do it, that will give you the kinetic energy, minimum kinetic energy which is required for the projectile to occur, I mean to react, occur the equation. I mean the projectile need this much energy so that the equation occurs. Now we will do it. Our Q is already given, mod Q is 4.0362, we have calculated it. Mass of projectile is also given, here it is 1.008665 in mu unit, and mass of target, this is this one, 18.998404, you cancel out. This will give you a value of 4.25 MeV. That means if your projectile, which was Newton for this case, have the energy of 4.25 MeV or above, then only the reaction occurs. Otherwise, if it has a 4 MeV energy, then the reaction will not occur. Okay, so the minimum energy is 4.25 MeV. So if your Newton has energy greater than 4.25 or equals to 4.25 MeV, then the reaction will only occur. If the energy, I am writing it as like this, energy of 0 and 1 is less than 4.25 MeV, the reaction will not occur. That's why it is called the threshold energy. Okay, so this is the minimum value of the energy required for the projectile, and we can calculate it like this, that first we will calculate the Q value of the given reaction and we will multiply that Q value, the mod Q value, with 1 plus mass of the projectile divided by mass of the target. Okay, just remember that. These are very small problems but very important. Okay. So this was the this problem. Now coming to another thing, that is monoenergetic gamma ray problems. This is nothing, I mean not very literature kind of word, literalistic word. Now what is I am trying to do, that you have seen while going through the material that for a accelerator we have a beam of projectiles, and at some position there will be a target, and that target, to keep that target in that particular position, we use some backing materials. And now if the reaction is like this, like the projectile is going, it is interacting with the target, I mean the reaction is happening and gamma rays are emitting. So gamma rays are the product. In that case, we need to choose the backing material in such a way that the detector can detect the gamma rays. If the produced gamma rays are already absorbed within the backing material, then the detector cannot detect it. Okay. So we can calculate what should be the width of the backing material which required, so that the detector can detect the gamma rays. On the other way, you can say, so that the absorption of gamma rays in the backing material is very less or the minimal, that we can calculate. Now it is a characteristics of the backing material which comes through some calculation, so that I will do it. Suppose in this problem that monoenergetic gamma rays are going, monoenergetic gamma ray, so suppose there is a reaction that has happened, and we are using a backing material of aluminum. Okay, aluminum sheet as a backing material of thickness is 10 centimeter. Now this material reduces the intensity of the beam. So the suppose if there is 100 in terms of number, I am saying, if there are 100 gamma rays produced in the reaction, then it is absorbing the 21 gamma rays, and the detector can detect only 79 gamma rays. So that's why we are telling that the intensity has been reduced. So intensity has been reduced by 21%. That means 21 of gamma rays has been absorbed by the backing material of aluminum. Then From there we can calculate the linear and mass absorption coefficient, which are the properties of the aluminum itself. By calculating this these values, the absorption coefficient, we can determine what should be the minimum thickness of the backing material, so that we can get, instead of 79 we can get 99 of gamma rays which has been produced. So that's why I thought this problem is important. So suppose for that gamma ray, that I0 is your original intensity. Okay. So this is a simple problem of absorption of gamma rays by any material. In terms of application, nuclear physics application, I am telling this backing material everything, but the problem statement is like some gamma rays are going through some matter, what matter that can be, and it is absorbing some of the gamma rays. So what will be the absorption coefficient? How we can calculate that? So I0, if I0 is the original intensity, I is the intensity of the after absorption, after absorption. So as I was telling, I mean all the problems I have taken from this book. Okay, so this book is available in my Google Drive link. If you can access it, that's fine. If you can't access it, just send me a mail in my email ID. I am telling it again. I will give you access just as soon as possible. Okay, so this book is very good book for the nuclear physics solution. This is a focusing only problems and solution, nothing else. And it is also, I mean, available in internet. You can yourself download it. Just search it by the book name, you will get it. Okay, so coming back to the problem. So I0 was the original intensity, I was the intensity after absorption by a thickness T. For our problem, the thickness is given as 10 cm. Now this I can be written as I0 e to the power minus mu t. So this is a exponential law which follows for the absorption case, that if you are starting with I0 intensity and the ray has propagated a thickness of T, then at that distance your intensity will be decreased by e to the power minus mu t amount. Okay. This is called the attenuation of gamma rays. Actually, this is attenuation. Maybe I am writing attenuation. Maybe my spelling is not correct, just check it. So this is the formula, that I equals to I0 e to the power minus mu t. That means what I am trying to say is, if this is the material I0 of the incident gamma rays, and suppose it has covered a distance of t, this is the t. Now the ray which will emit from this part, it will be I0 e to the power minus, so it will be I0 e to the power minus mu t. That is what I am trying to say, if the thickness is t. Okay, so I by I0 is e to the power minus mu t, and this mu is actually called the linear absorption coefficient, which is the characteristics or properties of the particular material, and by calculating that mu you can, I mean, okay, so I will tell it at the ending of the problem, you can understand it there. So I by I0 is given as 21 by 100, as 21% is intensity. Oh, sorry. So according to the problem, one mistake I have done. So the seat intensity has been reduced by 21%. It is not correct. It is actually 221%. Okay, so reduced by 79%. That was my mistake. That means you can do it by 21% also, by, but in my problem, in my rough sheet I have done it in this way. That's why I do it. That means 79 gamma rays has been absorbed and 21 has been detected, or that is coming out of the material. Okay, so pardon me for that. It is not by 21%. It was 221%. Okay. So that means now and your mu is not given, t is given as 10 semi. Okay, so 10 semi we are writing it as meter, because at last we will express it in terms of meter, and you can take the log from both sides and you can calculate. So your mu will come out as 15.6 meter inverse. 15.6 meter inverse. That means this is the linear absorption coefficient, and generally we express this as a mass absorption coefficient. So mass absorption coefficient can be calculated by mu by rho, where your mu is this mu and the rho is the mass density. So 15.6 meter inverse by the mass density of rho aluminum is actually 2700 kg per meter cube. This is the value, kg per meter cube. So that's why you will get it as 5.78 into 10 to the power minus 3 meter square kg inverse. This is your mass absorption coefficient. Now suppose before putting the aluminum, which is acting as the backing material, you just do experiment outside of the detector, that you have passed some gamma rays and you are getting 21% of gamma rays are coming out, what you have given at the initial. Then you can and you know the thickness, so from that you have calculated the mu. Now using this mu, it's again you that this mu is the property of that element. This is constant. I mean, this is a property which will be same in every situation. So you from that experiment outside of the detector or the accelerator, you have calculated the mu, and now you have this equation. So if you want to get 99% of the detected photon, then your I by I0 will be 99 by 100. Your mu you have calculated, your t is the only unknown in this equation. So from that equation you can calculate what should be the width, or the what you say that the thickness of the backing material, so that we can get most of the gamma rays which has been produced by the reaction. So that is why it is called a calibration type thing. We calibrate our backing material outside of the detector, and then we put according to our convenience the thickness in the backing part. Okay, so this is the just the application of that particular thing. So again I am saying, at first I have just mentioned it by, not by, it is true that 21% is the outcoming radius. The okay, so that was my mistake. So it has been decreased by 79%. Otherwise, I mean, I have started by saying that reduced by 21%. No problem will be that in that case also. In that case, what will happen? This I by I0 will 79 by 100. If I have started with the first thing, that by 21%. Okay, that was my mistake, and you will get the value of mu. Okay. So that was the main motivation of doing that problem, how we choose the backing material according to your linear mass absorption coefficient and mass absorption coefficient. Okay, now this is done. Now we will go to the maximum energy of beta particles. So in one problem you have seen that I have done the minimum energy required for the projectile. Now we will do the maximum energy of the beta particle. That means it is not the full thing, just let me write it. So suppose I have an equation like this: 7C12, it is decaying to 6C12 plus a positron, which is the beta ray, and a neutrino. So from here, how I can calculate the maximum kinetic energy of the beta particle? So this is a beta decay. Now this is actually putting the problem in a different language. Actually we need to calculate the Q value itself. What will be the Q value, the excess energy or excess energy you can say, that will be mainly shared by the beta and the neutrino. So neutrino will not take much, the beta will take the maximum energy, and that will be the kinetic energy of the beta itself. Okay, so this is the same problem, just the words has been arranged in such a way so that you may confuse. So actually we have to calculate the q value itself. So this type of problems is very important for exam purpose, because they change the form of the problem, and they at the end you have to just calculate the q value. So this is mass of 12 n, mass of 12c, mass of 12. Here I have taken, just let me check. Oh, so just I think I have made some mistake in my and just give me 2 minutes. I am just checking. Okay, so I think some mistakes I have done there. Okay, I have just instead of 7C12, that must be 7N12. That I am checking actually, nothing more. Physics. Okay, I am not able to find the problem right now from where I have taken that. So whatever, there may be some confusion. This may be nitrogen, 7N12. So there is a confusion that I will find if possible, but I am not getting the question. Whatever, so actually whatever the thing was, 7C12 or 7N12, the mass has been given. So the mass is, I think it was nitrogen. Okay, so that is my mistake. Minus mass of 12C minus 2Me. So I have shown you that how to calculate the beta plus beta decay q value, that I have already done. QB plus, yes, so this is the equation. So if you go to my first or second tutorial, you can find I have calculated the q value of beta plus, beta minus, everything, and it will be like this. Okay, so these values are given. This is 12.018613 in AMU unit. This is 12 and this is 0.008549. 0.0549 times 931.5 MeV. So you will get 16.31 MeV. So actually most of the energy will be taken by this beta particle. No, not the beta particle. So it will be divided by to beta and gamma and the neutrino. Now look at the question. I have said that maximum energy, not the typical only energy. So the maximum energy can be 16.31 MeV itself. What will be the release of the energy? All the energy is taken by the beta particle. That is possible. The neutrino is not getting any energy theoretically. I am saying, although neutrino will get at least some energy, but theoretically the neutrino is getting 0, and the division is like the 16.31 whole is going to the beta particle. That can be the maximum value. Minimum, theoretically it can be 0, but 0 is not possible. So we cannot calculate the minimum value, because we have to know other thing also to calculate the minimum value. That's why the problem is maximum value. So maximum value is actually the Q value of the energy. Okay, so there was some confusion. Just don't focus on that particular thing. Whatever the decay product, I mean the initial product, it will, the mass is given in my note. It may be a thing. We can see whether it is N or C by equating the proton number, Newton number, everything. I am not going into that particular thing. Okay, so this was the problem, and now I will just briefly tell you about the two about the two accelerators. So these problems, all these problems which I have done is from your previous course. All this we have done. Now cyclotron, for cyclotron it is a, I mean it is a accelerator, an accelerator of particles. Cyclotron and linear accelerator are the most two important accelerator, and there you can find some problems on this cyclotron and LINAC also. So what happens actually, you know that whenever a charge goes into a perpendicular magnetic field, there will be rotation. Okay, so if your magnetic field is like this coming out of the paper, you know, this is expressed like this, and your particle is have a velocity v. So if you divided it like x, y, z, your magnetic field is actually at positive x direction, your velocity is positive y direction. Okay. Then the Lorentz force that acts on the particle q v cross b, that means v is y cap, b is x cap, that means q v b y into x cap, right? And from the rule x y z, y cross x will give you minus z cap, q v b minus z cap. That means if you have a particle which has a velocity of v along positive y direction, this one, and you have a magnetic field which is coming out of the paper, that means positive x axis bx, then your particle will feel a force at minus z direction. So minus z means this direction towards the bottom of the paper. So that means this particle will turn, and it will go in a circular path, because at every point the magnetic field and the velocity is perpendicular, and the force is always make the particle to move in a circular path. So that is the main thing of the cyclotron. It is called the cyclotron. So the particle will move in a circle like this. Okay, so this will actually create a circle, okay, in the plane of the page, you can say, in the plane of the paper. So that is the main thing. Here you can also see that this is a figure of the cyclotron, where these half shaped things are called D. So these are called D. In some book it is written as DEE or D, whatever you can say. What it generally does, actually it is the source of the magnetic field, perpendicular magnetic field. That's why you can see that the round, I mean circular path is there, which is similar to this circular path. And in this position, in this separation, this is a separate gap. Here no magnetic field is there, but electric field is there. Suppose the particle starts from here, the electric field will be such a way that every time a particle comes into that gap, it will feel some acceleration. Okay, so suppose the particle at first was in this position, in this red position. Whenever it comes just out of that D1, it will feel a force which make it accelerate towards this D2. That's why the radius is increasing a little bit in every rotation. In the D itself, whether it is I mean in this part or in this part, in the D itself there is no acceleration. It is just giving a round like shape path. But whenever it is coming in the gap, this gap is the most important thing, this gap. Okay, whenever this particle, again this particle will go like this. Here the acceleration is happening in this gap itself, then it is following this path, no acceleration is there. Here it has reached this point. Okay, now the electric field of in this gap will be such a way, that's why we use a RF is actually change the direction of the electric field. So it will change the electric field such a way so that when the particle comes at this B point, suppose say it has started from A, when it was at A, the acceleration was toward D2. When it is at B, the acceleration will be towards D1. So in every time when it comes to that gap, the acceleration would be to the other plate. That's why the radius will increase a little bit in every acceleration. So the increase of the radius is happening in this part only, this gap, not in the D itself. D is giving you the round shape, and that gap is giving you the acceleration. This is the, I mean, this is how the cyclotron occurs. You can see it in any book, or you can go through any video. I have gone through some YouTube video. There are very interesting videos are available. You can understand how this acceleration is happening at that gap itself, only in that gap. Okay, so that you can do. Now I will not go into that part very deep. Now what I will do is, suppose now your particle, when you have reached a maximum radius, you cannot increase your radius, and it will go out of the accelerator. Okay, so yes, so when it is going through a circular path, what will happen, that there will be a force of mv square by r acting outside of the particle. It is just a propagation of particle in a circular path, and it will be just outside, and inside the F Lorentz is acting, which is this one. This is the Lorentz force. So F Lorentz is equals to mv square r in the D itself, because there is no acceleration in the D, it is only going through the circular path. So this condition is satisfied in the D, and if you write that QVB is mv square by r, from here you can calculate the r, mv by qb, what will be the radius, by calculating the magnetic field, by putting the magnetic field, mass and velocity, or if you know the r, you can calculate the velocity also. Now this is the radius, and if you calculate the frequency f, that can be v by 2 pi r. This is how we calculate the frequency for any rotating body. Okay, so just put that v in terms of just put that r, this r in terms of mv by qb. So qvb by 2 pi mv, and v will be cancelled out, that will be qb by 2 pi. This is very important. This is the frequency of the particle, and as I was telling you, that this RF oscillator acts in such a way that whenever the particle comes out of any D, it will feel a acceleration towards the other D, and this happens only when the frequency of this particular oscillator is equals to this f. This is the condition of resonance. So f of RF. So if your frequency of that RF, which is the oscillator, is equals to the frequency of the particle itself, then the resonance occurs, and only in that condition this happens, that whenever it comes out of any D, it will feel the acceleration towards the other D. I am again saying it is the condition of resonance of the particular synchrotron, cyclotron to happen. Okay, so this is a important thing, that our f RF should be qb by 2 pi m. Here you can see it is independent of radius. That is the main point. I am writing it in red, independent of radius. Okay, which is the main thing. And suppose it is going through acceleration and when it is at a point C, suppose it is the point C, it don't have any further space to go to a higher radius, then it will just go out of the D or out of the machine. Now from here you can calculate the maximum kinetic energy. What will be the maximum kinetic energy of the particle? So that is Wm, which we write half m Vm square. That means Vm is the maximum velocity, which is the velocity at the last circle, and m is the mass of that particular ion or atom, whatever that is. So m and Vm. So from here you can write Vm as Rm by QB, and there Rm Rm times QB, and there will be a m square. Now if you calculate, it will be q square b square by 2m Rm square. So Rm is the maximum radius. So for this particular figure, it is the Rm. This is the last radius of curvature. I mean radius of curvature. Here you can see this is Rm. Okay. So if you know the value of Rm for a typical cyclotron, you know the value. It will be supplied by the machine producer. So one example we will do from this particular thing, that our frequency which we have calculated from the centripetal force is equals to the Lorentz force, and from there we have calculated the maximum kinetic energy. Okay. So suppose an example of suppose a deuteron is going through the circular process of acceleration, and the magnetic field is suppose 1.5 Weber per meter square. It is given, and the extraction radius, which is the Rm or maximum radius, you can say extraction radius also. Extraction radius. So Rm is given as 0.5 meter. Now we have to calculate the frequency of the oscillator so that the resonance condition holds, and the kinetic energy, the maximum kinetic energy of the deuteron. Okay. So the frequency will be, as I told you, QV by 2 pi m. This one QV by 2 pi m, and your Q is 1. Just a second, 6 10 to the power minus 19 coulomb. C means coulomb, no, okay. B is 1.5 Weber per meter square, and 2 pi 3.14, and mass is mass of a deuteron, that is made of 2 protons minus 27. So just put it and calculate. I will not do the everything. So it will be 11.4 into 10 to the power 6 hertz. 11.4 into 10 to the power 6 hertz if you calculate it. Okay. So just a second. Yeah, just check this calculation. I have just put it at 1. Just a second. I will again check. It is the particle accelerator. Yes, so it will be, yes, I was right, 11.4 into 10 to the power 6 hertz, or you can write it as 11.4 megahertz. It will be the frequency of the oscillation of the electric field. Okay, and also maximum energy of deuteron we will calculate. That means this Wm. So that is Wm is actually Q square B square by 2m into Rm square. Rm is given in your question, and I don't have place. So Q is actually same 1.6 times 10 to the power minus 19 square. P is 1.5 square divided by 2m is 1.67 into 10 to the power minus 27 times 2. Okay. So and Rm is given in your question, that is 0.5 meter square. 5 square. If you put it, you will get 2.155 into 10 to the power 12 joule. And in this system, I mean in this thing, that when you come across particle accelerator, we generally express our energy in terms of electron volt unit. That is the general unit we use in our everyday life. I mean everyday life of the accelerator people, not you and mine. So it is generally written as electron volt unit. So mega electron volt, giga electron volt, whatever, but it should be in electron volt unit. Okay, so to convert joule to mega electron volt, that is 1 joule is actually 1.6 times 10 to the power minus 13 mega electron volt. So just remember this particular thing, and the conversion between joule and the mega electron volt is important. If you write this, perfectly fine, no problem. But maybe in your option you will come across with MeV instead of joule. Okay. Okay, so this was the problem. Like again, I am going through going quickly, that D, which is making the circular path, and that gap, which is the responsible space for the acceleration. That's why the due to the acceleration, the radius is not constant, it increases with every acceleration when it passes through that gap. And by calculating the mv square by r equals to Lorentz force, you can find the frequency of that oscillation, I mean the particle oscillation. And for resonance condition, this should be equals to the oscillation of the electric field in the gap itself, which is coming through this RF oscillator. So these two should match for resonance. So that's why this oscillation is actually the oscillation of the RF. So we know the expression of RF oscillation, frequency of RF oscillation, and the maximum kinetic energy will be the same like qb square by 2m rm square, where rm is the extraction radius or maximum radius of the cyclotron itself. Yeah, so from here you can calculate everything. And this type of problem you will mainly face from this accelerator chapter. Okay, now another thing I will do quickly, that is the linear accelerator or the LINAC, you can say. So this is the linear accelerator. The previous one was the circular accelerator, you can say, the cyclotron is actually. But here the acceleration happens in a straight line, linear way. So what happens actually? So suppose this S is the source, and a positive charge is there. It is just emitting a positive charge, and these are the different cylinder like structure which are added with the voltage difference. That means there is some alternative voltage. One is kept in negative, alternatingly the other will be in positive, and negative, positive, negative, positive, in this way. So when the particle is in this position in A, and suppose it is a positive particle, this positive particle will see a negative cylinder like structure is in front of it. That means it will feel acceleration towards that negative charged cylinder. That's why due to this acceleration, the energy will increase. So that particle now after some time has suppose come to this point after some acceleration in this first gap. Then when the particle will come out of this C1 again after some time, the polarity will be changed. So it is a figure when the particle is at this position, which is shown in the particular thing. Now suppose roughly I am drawing particle after some time has come in this position. This was the second cylinder. So at first it was in positive, but as soon as the particle is going to leave the C1 cylinder, the polarity of C2 will be changed to negative and it will be positive. So you can see in that cyclotron also there was a changing of polarity in the gap of the 2D, where the electric field polarity was changing by the RF oscillator that I have calculated. Here also the polarity is changed after some time. I mean here also the oscillating type of phenomena is happening. Whenever the particle is coming out of any cylinder, the, the polarity of the next cylinder just reverses, so that it will again feel some acceleration in this gap, in this gap, okay, in this gap, in this gap. This is how the acceleration happens in linear accelerators. After some time, this first 2 is there, the particle has come to the end of the C2 itself, the C3. In this step, in the second step, the C3 was in positive, but as soon as the particle in third step is coming at the end of C2, the polarity is again changed. It has been made negative, it is positive, it is negative. Again it will feel an acceleration in that gap, acceleration in the gap. Okay, so this is how the acceleration happens in the linear accelerator. And as you see that this acceleration will increase the velocity of the particles. So if you go from C1 to C2 for a constant time, it will move through a larger distance as the velocity has been increased. That's why your C2, length of C2 is bigger than C1. I mean C4 bigger than C2, C3 is bigger than C2, and C2 is bigger than C1. So that's why the length of the different cylinder is different, because with acceleration, repeated acceleration, the velocity has been increased, and for a particular time it will traverse more and more distance with increasing velocity. That is the main that is how the linear accelerator works. Now in this linear accelerator also, so let's think. Yes, so the linear accelerator, if suppose this length I will express as small l. So suppose if Ln is the length of nth cylinder, that means it is L1, it is L2, it is L3, and it is L4. Suppose in this way I have written that Ln is the length of n cylinder, and Tn is time taken by the ion to travel that cylinder. Okay, so Tn is time taken to travel in that particular cylinder, nth cylinder. So Tn will be equals to Ln by Vn. That is your time, where Vn is the velocity in that nth cylinder, right? Okay, so in that cyclotron case, I have told you that frequency of the oscillation of the revolution of the particle should be equals to the frequency of the RF oscillator, which change the current and the polarity of the 2D, not current, polarity of the 2D. Here the resonance condition is this Tn, it should be equals to 1 by nu, where nu is the frequency of the RF oscillator, which changes the polarity of the electric field, RF oscillator. If this resonance condition occurs, then only this type of condition will be fulfilled, that I told you, that when it comes out of a particular cylinder, at the time instantly the polarity of the other cylinder changes. So that is only possible if this frequency condition matches, that is Tn is 1 by mu, where mu is the frequency of the oscillation. Okay, and suppose that we have given some voltage difference, if that is V, so the energy, the total energy which has been calculated, so that will be, that means every gap will give you QV amount of energy to that ion. And if there is n gap, the energy gained of the particle will be NQV, or total energy, because n is coming for the number of cylinders and QV is energy gain in each gap. Okay. And if this is the energy gained by the particle, so I will write it as Vm. So Vm is just notation. Now if it is the total energy of the particle, that kinetic energy of the particle will be equals to potential this. So this is capital V, okay, this is the voltage, and this is the small v, this is the velocity, half m v n square. So the velocity of the particle when it will come out of the linear accelerator, I mean by getting accelerated in the nth cylinder, that will be equals to the n cube Vm, energy gained by the particle. From here you can also write that your Vn, which will be the maximum velocity, as 2n cube Vm divided by m. So here you can see that your n is fixed for a particular accelerator, your q is constant, Vm is depends on you, how much voltage you are giving through the RF oscillator, and m is the mass of the ion. So this the values of the right hand side, you know everything, and from there you can calculate the maximum velocity which can be achieved by the particle. Okay. So this is how the acceleration happens. The main thing for any of the accelerator is the acceleration which is coming due to the electric field, applied electric field. For this linear accelerator, it is applied in that successive gap of the cylinders. For cyclotron, it has been applied in the free space of the 2D. So that is the main reason why the acceleration happens. Now one very small problem we will do from this linear accelerator. These problems are very easy to do. Okay. So suppose I will tell while doing the problem that the resonance condition so the resonance condition, as I told you, that 1 by nu should be ln, which was the length, by Vn. Okay, that means you can write your ln as Vn by nu, and Vn, which is written in this way, that is the total energy, that is the E. Okay, so Vn can be written as 2E by m. E is the energy gained by the particle, which can be written as n cube V also. So E can be written as n cube V also. This V is the voltage. Okay, so if we put that expression of V, we can find that it will be 2E by m, right? Okay, now we want to calculate the length of nth drip tube. So those cylindrical type structure, these are called the drip tube actually. Okay, so we will calculate. So ln we want to calculate. Now for this problem you should be given the nu, the E and m. So the nu is given, I will tell you, because the problem statement is very big, I will not write everything. So where is it? Yeah, so the energy E, it is given as 100 MeV. That means in the linear accelerator, the particle has gained an energy of 100 MeV, and this nu is given as 500 megahertz. These are given in your problem. So from that you can calculate the ln very easily. It is 500 into 10 to the power 6 hertz, because we have converted the megahertz to hertz. E is 100 MeV. Also from MeV we will go to the joule. Okay. And that m is, here we are considering the protons. Okay, so protons has mass of 1.67 10 to the power minus 27 gram, and to the power half is there. So if you calculate, it will give you 1.38 10 to the power 8 divided by 500 into 10 to the power 6 is 0.276 meter. So 0.276 meter is the length of your last tube, that is nth tube. So the main thing was this: you have to use this particular expression, and I mean, if you have to calculate ln, then nu and e will be provided. If you have to calculate the e, then your nu and l will be provided. Something will be provided, and from there you have to calculate one particular unknown. Okay, so that is the main thing, but the main understanding is lies in this expression. Now, and again we will calculate that what will be the acceleration, what will be the energy gain of the particle in the first tube itself. So we are only in the first tube here, and we will calculate what will be the energy gain in that first tube. Okay, so that we will write as E0 as 1 by m v0 square. V0 is the velocity in that zeroth tube, that means first tube. Okay, and v is also can be written as this, you can see. So Vn is ln by nu, that means V0 is L, just a second, Vn is nu ln. So here Vn is nu ln, that means V0 is nu L0. In this way you can write it, half m nu L0 square. Right. And here given, so given L0 is 50 centimeter, it is given, that means 0.05 meter. Okay, and nu I have told you, this is the same problem. Okay, another part of the problem, 500 megahertz it is given. So m is 1.67 10 to the power minus 27, nu is 500 10 to the power 6 hertz, and it is 0.05 meter. And if you calculate this thing, okay, so the yes, everything okay, so the result will be in joule, because it is in SI. We have done everything in SI. Just a second. So the result will be whatever will be the result, we want to convert it in MeV. That's why we will divide it by 1.60 10 to the minus 13. I am not doing all the calculations. So just whatever you will get in this from this expression, divided by 1.60 10 to the power minus 13 to convert it into MeV, that will give you 3.26 MeV. So the particle has a energy of 3.626 MeV in the first dipped tube or first cylinder itself. It has not covered the whole distance by now. I mean, it is the energy gain in the first cylinder only. Okay, now 3.26 MeV. Okay, so the funny part, another part is that here in the question it is given that the maximum energy which has been, I mean, maximum energy is gaining by that tube, by the particle in that tube is 100 MeV. So 100 MeV is your maximum energy, the final energy, and E0, that is the initial energy, you can say it is 3.26 MeV. So the energy gain from here you can calculate 100 minus 3.26 MeV. That means the total energy minus the energy in the first tube. Okay, it can be 96.74 MeV. So this is the energy gain by the particle, net increase in energy for protons. Here particle is proton. Okay. Now this is the energy gain, and this energy gain has been happened due to the acceleration in different gap itself, right? Because I have told you that the energy gain is happening in these gaps, So if the energy gain is 96.74 MeV, we can calculate how many gaps are there in that particular linear accelerator. Okay, because increase in energy in each gap is QV. If you write Q, I have told it previous time also, and your V. Okay, so here you need to get the value of V, which is the voltage, and it is given the voltage is 1500 kV. It is given in the problem. So if I took that 1500 kV means 10 to the power 3 volt, it will be in joule. It will be 1.5 mega electron volt. Just again as previous I have done, just divide the result with this value and you will get the MeV from Joule to MeV. So 1 point MeV acceleration is giving by each gap. The total energy gain is 96.74 MeV. That means this is the total number of gaps in the linear accelerator, which is approximately 65. So you can calculate this type of small things. Some value will be given, other you have to calculate, but the whole problem based on this single formula ln is 1 by mu 2 e by m. It can be written as 1 by mu equals 1 by nu equals to ln by vn also. This is the different type of expression of the same thing. Just remember this particular formula. From there you can calculate everything associated with the linear accelerator. Okay. So two type of accelerator I have mentioned, the most important ones, that are those are the cyclotron and the linear accelerator. In the first, the acceleration is happening in circular way, and in the linear accelerator it is in a straight line. Okay. So I will not go much details of the accelerators anymore. If required, I will see in the last assignment problems. Okay. So this was the thing. Now these are very small problems. Okay. Now one problem I have not done it. You can remember that's 3. This one, I think it will be better to do it in the next class. Okay. So this problem I am not doing it today. Then you will understand it in a more good way, or it will be beneficial for you also. Okay. So this problem I will do it in the next class. This is a very good problem also. This takes into consideration the detectors, the position of detectors, reaction cross section, everything. Okay. So as I have not gone to the detector part I will go to in the next class. That will be the last tutorial. Then I will cover this problem. In the meantime, you can go through some of the problems of this book also. Again, I am telling, it's a very good book. Now another problem I will do, the last one, which is from the semi-empirical mass formula that we have done already. So it is a very nice problem. Like we have given 3 types of element: 2He6, 2Be6, 3Li6. These 3 elements we have given, and the question is asking that which one is the most stable. You can find this type of problem in everywhere. Which one is the most stable from this among these 3 elements. Okay. So that we will do from the semi-empirical mass formula. Our binding energy was written as AVA minus AC a to the power 2/3. Oh, it is AS. The surface term AC Z into Z minus 1 A 1/3 AN, that is the asymmetry part. Okay. And there was a pairing term, which in the last class I have used this type of term, which is so in that drive link which is shared by that book, in this drive link you will find another book is there, which is a very good book of nuclear astrophysics. So if you want to go some part of that book, that is also will be very useful. Okay. I mean this type of expression I have taken it from that book, which is in the drive itself. So please go to that book. Okay. So this was the our semi-empirical mass formula. Now here also, as we have done in our first problem, we will just approximate Z into Z minus 1 as Z square. Okay. This is the approximation. Now for most stable case, for most stable nucleus, EB must be maximum. If the binding energy is maximum, that means the nucleus is stable for a given mass m. For a given mass number a. So for most stable nuclei, EB must be maximum for a given mass number A. Mathematically, it can be written as dEB by delta Z, when your A is constant, is 0. Okay, so we differentiate our semi-empirical mass formula with Z, keeping the A constant, and U equals to 0. That will give you that is the condition of maximum stability. Now we will do differentiation with respect to Z. So you can see first term has no Z, it will not contribute in the differentiation. This will also not contribute. So these two term will not contribute. Here the Z is there, that means the third term will contribute. It is smaller. It will also contribute to Z, and it will not contribute again. So the main term which will contribute is the third term and the fourth term, that is the Coulomb energy term and the asymmetry term, and all the other terms are 0, because we are doing the differentiation with respect to Z. Now if you do this differentiation of that particular two term, you will get 2AC A minus 1/3 Z plus 4AN A minus 2Z A inverse is 0. That you can do it, just differentiate the third term, which will give you 2Z. Okay, so this 2 is coming for the 2Z, and similarly the other terms, and this is equal to 0. Now it will give you 4AN minus 8AN A inverse Z is equals to 2AC A 1/3 Z. 4AN plus AC A 2/3. Just it is algebraic calculation, you can do it to be 2, but the result is interesting. Okay, so you can write your Z as A divided by 2 plus AC by 2AN A to the power 2/3. And if you use that value of AC and AN, which I have written in the last class, right now I don't remember that. So if you just put those value, you will get expression like this. This is the most important formula of the semi-empirical mass. Most important expression of associated with the semi-empirical mass formula. 0.15 A to the power 2/3. This is actually giving you the Z number, the value of Z, which is the value of proton number for a mass number A, which tells you which element has the Z according to this law, to this particular law, that particular element is most stable. Okay, now we have given that it is the actual formula. Now we have been given that helium, beryllium and lithium. So for helium, beryllium and lithium, the A is very small, they are light nuclei, and the second term, which is 0.015 A to the power 2/3 in the denominator, that will contribute only when the A value is very high. That means for light nuclei, that means A is low, this A to the power 2/3 0.015 is negligible actually. This is for light nuclei only, not for higher nuclei, higher mass nuclei. In that case, you have to use the total expression. I am just doing some approximation for light nuclei. So you can write from here Z approximately as A by 2. So those elements are stable which has the proton number is exactly half of the total mass number. That's why you can see 6C12. 12 is A, A is 12, Z is 6. It is following this formula. It is a stable element. 8 oxygen 16, it is also following Z is equals to A by 2. Okay, so this type 2Ag4, this type of elements are stable because of this. I mean, why they are stable, I have calculated it from the semi empirical mass formula. Now the questions, the element which is given in our question, that for the first thing this equation does not vary. For this case it is Z equals to A by 3, but we need A by 2, right? We need A by 2 for the stability. So this is not stable. Here also Z equals to A by 3, not stable, but here you can see Z equals to A by 2. So this is the most stable element between among the 3 elements which are given in the question. Okay, so this is how we calculate the most stable elements and the associated proton number for the most stable element with the constant A, because in the question you have seen that all the values of A are 6, just the Z number has been varied. So we have compared among these elements which are same A equals to constant but different Z, and we have calculated which one is the stable one. So 3 Li 6 lithium 6 is the stable one, which is exactly coming from the semi empirical mass formula. Okay, now this was the problems which I wanted to discuss before your exam. I will try to find some more problems in the next day also before your exam. Now very quickly, if I go through the questions of your assignments, this was just theoretical assignments. So the first one was, how does the probability of the full energy deposition depend upon the atomic number of the material? It is actually Z to the power 4.5. Okay. Now the second one, which of the following process is most probabilistic for high energy gamma rays? High energy gamma rays means the gamma rays has enough energy to go through the pair projection, because at low energy the photoelectric effect, Compton scattering, all this happens, but when your energy is increasing, the pair and it is crossing the threshold value of pair projection, which is for one pair to be produced, it is 1.02 MeV actually the threshold energy, because it is the rest mass energy up to 1 electron and 1 positron. So that is 0.51 MeV, I think. So for 2 it is 1.02 MeV. So if the energy is greater than that, that means we are going to very high energy gamma rays, so the pair projection mainly happens. If the energy is less than that 1.02 MeV, that means lower energy gamma rays, then this photoelectric effect, Compton scattering and Rayleigh scattering takes place. Okay. Third question says that which one of the category of the detectors has the best. So detector part I have not done it yet, but I will tell you the answer. This is a semiconductor detector. I will cover it in the next class. Now the frequency of oscillator of a cyclotron is so frequency is given, F is given, radius is given, I mean Rm, the radius of Ds, which is the maximum radius. Calculate the operating magnetic field for accelerating electrons. So this you can calculate. I have shown you everything, that F is F can be written as, so if I go to the cyclotron part, F is QB by 2 pi m, right? So just do that. F is equals to QB by 2 pi m. Q you know, B is you have to calculate the B. R is also radius is given. From that radius you can calculate the yes, just a second. Radius is given 0.7, m is given, q is given, and f is given. Yeah, so you can calculate the other things in terms of all the f means frequency. Frequency means 1 by, so f is frequency, it is actually 1 by t. So you have to calculate the operating magnetic field. Just a second. So 77, yeah, R. Okay. So I have written F equals to QB by 2 pi m. You can also write that in terms of R. Okay, because you know that R is, what is R? Yeah, R is mv by bq. So from this you can write R in terms of B and Q also and V itself. So just do that, you will get the result. Today it is very I mean almost 8. I will do it in the next class, I mean line by line how to solve this. Otherwise you can do it by yourself. Okay, so you will get the result as 4.28 G Gauss. I will do it now. The second is how much energy does 12C ion in a 6 plus charge stage acquire after acceleration through a linear. Here you can see it is a linear accelerator question, and the potential difference is given. I have told you that the the energy gain is actually QV. Okay, so Q is given 6E and V is 10 to the power 10 million volt, that is 10 into 10 to the power 6 volt. So it will give you in terms of electron volt, just if you do it. So it will be 60 into 10 to the power 6 electron volt, that means 60 mega electron volt. Just very small problem, equals to QV. Now again the 6, a linear accelerator, that is also a linear accelerator problem designed to generate a beam. So 80 MeV is the maximum acceleration, has 22,000 accelerating tubes separated by gaps. What average voltage? Okay, so the total energy is actually N and QV, NQV, that is the total energy I have told you. It is given as 800 mega electron volt. So N is there. In this question I will not put the value of Q, I will just put Q as E in electron volt, an electron charge unit. Okay, and the V is given as, also we have to calculate the V, right? So V is there. Now if you do it, V is actually, so 800 and N is 2000. So N will come downwards if you calculate. So it will be 0.4 megavolt. V is 0.4 megavolt. So actually how it is how it happens that this volt and this electron charge, it is associated to give you the electron volt unit. Okay, here 800 mega electron volt means it is 800 into electron into megavolt. From here that 800 mega electron volt comes. So that's why this E from both sides is cancelled out, and your V is actually 800 megavolt divided by 2000, which is 0.4 megavolt. Okay. Now the 7 is also the cyclotron problem. So as I have done it, you can also do in the same way. So it can be done by like this: m equals to qb by 2 f pi. So f is actually 1 by t or n, whatever you say. I have written f as n, I think I forgot that. So whatever, or new whatever. So f is the frequency. So m equals to qb by 2 pi f. Okay, and if you put your you can see your f is given 16,000 hertz, 1600 hertz, sorry, and your Tesla, which is the magnetic field. So B is given, F is given, Q you know, just put it in the equation and you will get the result. Just a value putting equation, and it will give you 2.5 10 to the power minus 23 kg. Okay, m equals to qb by 2 f pi. So this problem also can be done like in this way. So m equals to, what was that, qb by 2 f pi, qb by 2 f pi. Okay, so 12 megahertz, which is the value of f, is given. 70 semi, the 70 semi you have to calculate it from the that r equals to, what was that, mv by qb. So r equals to mv by qb. Okay, just let me see it. qb mvr. I think there is some other thing also. Okay, I will come to this problem. Today I am exhausted actually. So 7 is done. 8 is actually, it is also a theoretical questions. Which of the following modulus is used to obtain an amplified and shaped linear pulse from a linear charge pulse? Amplified and shaped linear pulse from a linear charge pulse from the detector. So the answer is actually D. It is a theoretical spectroscopic amplifier. Then 9. What length of the conventional coaxial cable is necessary to shift the position of the prompt peak in the so this I will 9 and 10 these two, and that problem which requires some calculation I will do it in the next class. Okay, today it is too much. I mean, oh sorry, not 3, 4. So these 3 questions along with the last assignment I will cover it in the next class. I think all the problems which are the extra problems I tried to do it today. I think you have just try to understand all the problems. These are very small and very little problems and very interesting. Oh, with these 3 problems I have another problem which I have to cover in the next class, that is this one, the extra problems. Okay, so these 4 I will do it in the next class. Okay, so for today I think we can end the meeting, I mean the class, and if you have any question or if you want to access those 2 books, just send me a mail, or if you can copy that email, I mean web site, just do it. The access is already given there. Okay. So thank you. We will meet next for the last tutorial next week, Tuesday. Thank you.